Hello, I'm David. I'm the coordinator of the Maths Learning Centre. It's semester 2, 2018, and this is the first Maths 1B of the new era. This is a revision seminar before the exams, and that's enough of that. Okay, so I promised myself and at least one other person that I would talk about phase diagrams because I myself was confused about them at the time, and that's something that's new in Maths 1B this semester, so I'm going to talk about that first. All right, there we go. It's to the right, but that'll do. So, I've got this right. A differential equation is an equation that relates the derivatives of a function to the position that it's at. So that could be the x-coordinates or the y-coordinates, and they're related somehow to the derivative. So all right, so a differential equation relates the derivative of something to the values of x and or y. And when you have a differential equation, your heart's desire is to figure out a formula that tells you what y is when you know what x is, or t, or whatever the variable actually is. And the reason they exist is that a lot of physical situations in, say, physics or engineering or chemistry or biology are easiest to describe in terms of how they change rather than how they are. And changes is what derivatives is about. And so that's where they come from. There you go. So there are types of... We'd like it if we could get y equals a function of x. That's what we would like. But sometimes that's not possible. Or at least, yeah, not as possible as we would like. Sometimes that's a lot harder than we want. And sometimes we don't really care what y is as a function of x. We just want to know what might happen eventually. So there are times when we just want to know a general idea of what might happen to y, as opposed to exactly what it is at any given moment. And that's where the phase diagrams come in. So we might settle for knowing what might happen to y as x gets big. So perhaps my differential equation describes the concentration of a certain chemical in my chemical reaction, and I would like to know if I left it for long enough, what would that concentration become eventually? Or maybe the differential equation describes the populations of certain animals in a certain place, and I would like to know, as the time goes forwards, what will those populations become? Hopefully not zero if I wanted to save them as an ecologist. So that's the general idea, as far as I can tell, of what we're going to settle for when we do our phase diagram. So phase diagrams are a way of us figuring out what happens to the y if my differential equation is specifically in the format dy on dx or dy on dt in particular, is a function of only y. And I'm going to put it as a t because we're going to imagine it in terms of time So phase diagrams help when we have a thing that's dy on dt equals function of y only. So we know that the current rate of change of y is related to the current value of y, but it's not related to what the time is at the moment. So if the current value of y is really high, then maybe it will be moving quickly, and if the current value of y is low, it'll be moving slowly, or possibly vice versa. But it doesn't really matter how long it's taken to get to that point. It will move at the same speed based entirely on the value that it currently has. That's the idea. So that's what phase diagrams are for, as far as I can tell. As I said, this is new this year, so I'm still figuring this out. Okay. So it might be easier to do with an example rather than any other way, but I just wanted to talk about it so that I was clear in my head why we care about it. I'll come back to this in a minute. Give me a moment. Right, I just wanted to look up the example that I had a picture of. Okay, so suppose we had this. So this is telling me, so just so that we can get a handle on what this means that if the current value of y is, say, 4, then dy and dt is 4 times 4 minus 1 times 4 plus 1, which is 4 times, which is 60. So that's telling me that if t moves forward a teensy bit, then y will go up by 60 times that teensy bit. So if the change is t is, say, like 0.1, then we expect the change in y to be 60 times 0.1, because that's how derivatives work. The change in y should be the derivative times the change in t, which is 6. And so we expect in 0.1 of a second the new y value will be 10. Four plus whatever it was afterwards, and so it should be 10 now. And now, if I go 0.1 of a second beyond that, it will be even faster, and the y is going to get faster and faster and faster and just keep getting bigger and bigger and bigger. Okay, so if I start at y equals 4, then at any moment I can make an approximation for what's going to happen to the y next based on what the current value of y is. And that's the idea of a differential equation. Some differential equations, it's based both on what the time is and what the y is, but this one is based entirely on what the current value of y is. Okay, so if I had chosen a different starting place for y, then I might have gone in a completely different direction. If I choose a small enough number for y, then maybe if it was negative, then y would keep going down. So what I'm going to do is I'm going to jump over here onto the computer. This is Desmos, or Desmos, depending on how you want to pronounce it. The Americans pronounce it Desmos, and that's who I learned about it from. So what I have here is a picture of, this is the time. Time's going to move forwards, and this is the current value of y. So if I put the y, if I put the y, say, there at 1.2, and I press play, well, the y shot off the edge of the screen. It just got bigger and bigger. Okay, let's bring back to time equals 0. If I put the y there at 1.1, took a little while, but it got there. It went very fast, very quickly. I might slow my time down if that's in a second. If I put the y over here, then it just got closer and closer and closer and closer to 0. as time moved forward, that's what happened to the y. And no matter how close I put it, where is it? It does. If I put it at like 0.99 and then press play, it still goes down there to 0. And if I put it over here, put time back to 0. If I put it over here, then it also goes towards 0. So different places where y is, I'm just tracking what the y value becomes as time moves forwards, and it's easier to do it on a horizontal axis when I do this. So what will happen is that various places, the y, if I start in that spot, will tend to move towards a certain direction. So if it's out here, over on this side, damn it, over on this side, it'll move outwards. If it's between these two, it'll move towards the 0. If it's here, it'll still move towards the 0. And if it's over here, it'll move downwards, away from us that direction. Let's just check that. Yes. Okay. That's what happens to the y in terms of just following the value of the y. Now I can actually see what that looks like as a function as well. And I think it's in here. Just let me... Nope. Where are you? No. I can't. I made this when we first did it and I've forgotten how we did it. No, that's okay. Ah, there it is. Okay. I'll just turn this axis off. Okay, good. All right, so this is the function now drawn as a proper function where the x-axis is whatever the x-axis is, and the y-axis is the y-axis. So this is the time axis here, and as time moves forward, the y keeps going down and down and down. But if the y started a bit higher, the y keeps going down and down and down. But there comes a point where nothing will happen at all, and then above that it just goes up from there. So if I start at different places, it goes, the shape of the function is different. And what we're looking at is where it goes when we come to this end over here. I find it easier to think about it not as the graph of the function, but as the moving point. But you may feel differently about that. Okay, where was I? Oh, come on, you stupid machine. Right. So, the point is we want to know, given various starting values, where does it go? And we can tell that by analysing this function. If this function is positive, then for a particular value of y, then just like this one, that will mean that as t moves forward, the y will go up. And if this function is negative for a particular value of y, then that will mean that as t moves forward, y will go down. And so what I need to do is investigate when is this function positive and when is this function negative. So I look at it and figure out where it's equal to 0. It's equal to 0 when y is 0, when y is 1, and when y is minus 1. And then I try and figure out whether it's positive or negative in various places. So you can, if you want, just attempt to draw, just inverted commas, you can draw the graph of that function as if it was a function of x, and know whether it's positive or negative. And the other thing you can do is just sub in various values of y so that you do a sign diagram like you would do for a derivative. So I can see that if y was 4, it came out to be a plus over here. We did that one already. When y is like a half, I've got a half times a half minus 1, which would be a negative number, times 1 1/2. So this is negative here. If y is negative a half, I've got minus a half times minus 1.5 times a half. So that's positive there as well. And if y is like minus 2 times minus 3 times minus 3, that's negative there as well. So I can do it as a sign diagram if I want. So I got this by subbing in values of y. The other way is to notice that this is the biggest power of this is y cubed, and a cubic function in general goes up, down, up. And so you can know that when it's down here it's negative, up, positive, down here, up. So that's the other way of doing it. Okay, so that's a sign diagram for the values of y. But what we normally do is we don't draw it that way. We draw it so we've got a picture here which has plus minus plus minus. We normally draw it with arrows on it to say which direction the y is going to go. So these are the values of y, and this says that the derivative dy and dt is positive if y is in this zone. So if dy and dt is positive, then it will increase when I'm in this zone, and so it will go that way. And if dy and dt is negative, the y will decrease, and so the y will go that way. And if dy and dt is positive, it will go that way. And over here, dy and dt was negative, so it will go that way. So this is called a phase state diagram. Or just a phase line. So up here, this is a sign diagram for the value of that function. This is a phase line which tells you where the value of y will go. Okay, so now I can tell that if I choose my y somewhere between 0 and 1, then as t moves forward, the y will approach 0. So if y of 0 is, say, 0.5, which is in here, then the limit as t goes to infinity of y of t will be 0, because it will start here at 0.5 and it will move downwards towards the 0. And if y at time equals 0 is 1.3, then the limit as t goes to infinity of y of t will be, well, here we are at 1.3, it'll keep going up. So technically it does not exist, but it's going towards infinity. I think your lecturer writes equals infinity in this course. Different lecturers have different beliefs about whether that's an okay thing to write, so I just wanted to check. I am mostly uncomfortable with it, but it's okay. Why is what the case? Oh, well, infinity is not a number, so I can't say this is equal to it. That's my problem with it. But I'm all right. We write all sorts of dodgy things in maths, so like the derivative notation itself is just a basket case. So, yeah. Okay. Sorry? Both of them. They're all bad. All derivatives are badly written. Okay, so that's how phase line works. And just an important one, if y of 0 is 0 already, then the limit as y goes to infinity of y of t will be 0. Because I started at 0 and it just stays there. In fact, it would stay here too. Even though everything moves away from the 1, if I'm exactly at 1, it won't move at all because the derivative will be 0. So it doesn't move at all. But if I move a teensy bit one way or the other, it will move away from the 1. Okay, so these things are called, just a second, they are called critical points. So I'm just going to label my diagram. They're called critical points because they are places where the derivative is 0. That's what a critical point is. And they tend to be called stable or unstable depending on whether the arrows are pointing away from them or towards them. So what we have here is we have a stable one, and this one's unstable, and this one's unstable, and it's because the arrows are pointing away. Unstable means that if I moved it just a wincy bit from the 1, then after that point it would move away from the 1, no matter which direction I went. It is possible to have some that are neither unstable nor stable. So here's a challenge. This is fun. Think of a function of y that I could put here so that I get an unstable critical point.
What about a function that's flat on the x-axis, like it doesn't touch by this, like just flat?
Okay. So are you... Sorry? Okay. Y cubed? Has to be a function of y. Well, let's see what happens. So the only place where that is 0 is here, and that function does this. So it's still positive here and negative here. Okay, good. So my phase diagram nope, that's an unstable point. Sorry? Y to the 4. Okay, cool. Okay, so you guys had some lovely expectations of what you think should happen, and it's very useful to have those expectations challenged. I didn't know what was going to happen, but it turns out that it's not to do with whether it flattens out, it's just to do with whether it's positive or negative. So why have you chosen y to the 4? I've had several people I've heard that say that if I did y to the 4, then it's still 0 here, and it's positive on both sides. Well, let's see. Technically, you don't have to draw both of these, but I feel better about it. So, like that. So this is neither. The reason it's neither is that if I move a little bit this way, then my y will keep going outwards. But if I move a little bit this way, it'll come back towards 0. So it's like it's stable on one side and unstable on the other. And so we just say it's neither. Yes?
Are neither critical points symmetrical locally around that critical point?
Can you say that another way? I'm not sure what you mean.
Like, you know how the y to 4 is
Yeah.
symmetrical around
Yeah.
that critical point? Could you have one that's not symmetrical locally around that critical point?
Yes, you totally could. It could be faster in one direction than the other. And I'm trying to think of one. Give me a second. Oh, that's exactly what I was about to draw. Good thinking. So this function happens at 3 and 0, and it's got a... and it's sort of steeper here than it is here. And so when I do my phase diagram, it's negative here, still negative here and positive here, so it's going that way, and that way. So we have an unstable one over here at 3 and a neither at 0, but this one is moving slower than this one is when I'm close to 0. Because the derivative is sort of deeper here than it is here. It's steeper on one side than the other. I don't know if that answers your question or not.
So the second derivative test will be 1, not 0.
Ah, there's a second derivative test, is there? Okay. I didn't look that far in the book because I didn't need it. Let me just look this further. Ah, you mean this thing. Right. Okay, so it is possible to have... So you're wondering, is it possible to have one that is... Good question. I don't know. I'm just going to look that up in a second. This is new to me this year, so still figuring this out. Oh, I better be consistent. Okay, so you're telling me, just a second, there's a thing with a second derivative. So we have a phase. We can figure out when the critical points are by figuring out when this is 0. And then you're saying that there's the second derivative should tell me whether it's stable or unstable, apparently. Why would that work? So if we did the derivative of this with respect to y, the second derivative of this would be that with respect to y times dy and dt, but the dy and dt was already 0. Anyway, I have to think about that. So just a second, there's apparently a second derivative test. Well, just a second. So it goes like this, if this is a function of y, then at a critical point, if f dashed y is positive, then it's unstable. And if f dashed of y is negative, then it's stable. So we're saying that if that derivative comes out to 0, then it could be stable or unstable or neither. Interesting. So I just want to check something. Okay. So I'm just going back to the function I had before. And that's the derivative of that original function. And at 0, which doesn't tell me whether it's stable or not, and at 3, 3 times 9 minus 3 times 6 would be 9. And so that's unstable. That checks out. Cool. So you're wondering, can we arrange it to have that derivative being 0 and it's still... Yes, we did it already. The derivative of this function is 0 at this point, but it's still an unstable point. Even though the test fails, it says that if it comes out to 0, that doesn't mean it's neither, it means it could be any of the 3 options. Okay. It seems to me that that derivative test is a waste of everybody's time. Because just like the second derivative test for maxima and minima is a waste of everybody's time. Because you could just do a sign diagram. Anyway. Okay. So let's just see what happened just then. Thank you for bearing with me while I was figuring this out. My hope when you see me do this stuff is that you can see how you might do the same thing. So my phase diagram is designed to help specifically when I have a dy and dt or dy and dx or whatever is a function of y only. And then I figure out where it crosses, where it's equal to 0, and I can do a little sign diagram. I don't have to do it, I can do it straight with the arrows. And then if the arrows are pointing out, it's unstable. If the arrows are pointing in, it's stable. And if you have one of each, then it's neither. And that's about it. And if you have a y in any particular zone, then you just follow the arrow, and that tells you what the limit will be as t goes to infinity. Sorry? When is it neither? When you have one arrow pointing towards it and one arrow pointing away. Here. But in terms of the function itself, I don't know. So the thing is that neither doesn't really tell you anything about the shape of the y function in terms of t, the normal way of drawing that graph. It doesn't really tell you anything. It just says that if you start the y at a certain place, it'll just move away from that. So the idea is that if someone has already solved your differential equation for you, and they go, hey, look, my starting value was y equals 2.3, and when I run it for a while, it went to y equals 10. You go, oh, that's cool. And you think, well, mine's 2.36. Is it still going to go to 10 or is it not? And if that was an unstable point, then it would move away from the 2.3 and not necessarily in the same direction. So that's the idea. If you know whether that point that someone else had was near one of the critical points, you'd have to know which side of the critical point it's on so you knew where it went. I'm going to move on. Just remember that if I don't answer your question here, the drop-in centre is open all week, so you can still come and talk. Well, we investigated that quite well. I'm happy. Okay. Good. So, series. That's what we're going to talk about? Who did I borrow this book from? Okay, just so that I don't forget. Okay. I'm just going to take a quick look . Yeah, okay. All right. Right. So, I'm just going to step back a little bit. If the lecture notes are the order that your lecturer talked about it in, which might be true this semester, but in the future, if you're watching from a future year, then it might not be true, but all the same. They talked about sequences first. So there's this idea that you can calculate something and just write down this list of numbers that goes on forever, and they'll have a pattern to them. So a sequence might be something like 1 and then a half and then a quarter and then an eighth and then a 16th forever. That's a sequence. It's just a list of numbers that goes on forever, and usually there's a formula that tells you what the number is when you're up to a certain position. And so, just checking something. Yeah. So it's tradition to call this A. So you might say that this one is A1, and this one is A2, and this one is A3, and this one is A4, etc. And then usually there's a formula that tells you what A whatever is, and so it's something like AN is 2 to the n minus 1, for example. So that's an example of a sequence. Great. So some sequences, if you follow them along, they approach a certain number. This one, the numbers get smaller and smaller and smaller. You get a 16 to 32nd, eventually, and it'll end up being 0. And you can talk about the limit of this sequence. Because those numbers themselves keep getting smaller and smaller. That's a sequence. A series is what happens when you add up a sequence. Patience. I will get there. A series is what you get when you add this up. Forever, whatever that means. And that's the written with a sum notation sign. That's a series. So one difference is that you can't say that this list is equal to that, because this is a list of a large number of different things, and none of them are actually equal to that specific formula. They're all to a different instance of it. But this thing is a single number, and so it's equal to this thing. And that's a series. And mathematicians go, yeah, I get what I mean. Well, I think I get what I mean by adding up something, infinite, the entire infinite string of numbers. Only I don't, and so I better be really clear about this. And what they actually do when they think about a series is they don't really think about it this way, but when they define it, they think about it as a sequence of what the sum is so far. So it's sort of like a running total. I will call it a running total. There's probably a name for it, which I will look up in a second. 1, and 1 plus a half, and 1 plus a half plus a quarter, and 1 plus a half plus a quarter plus an eighth. And I have this running total that as you keep saying another number in the sequence, I'll add them up as I go. And that running total is a list. And I can talk about a series converging of being equal to a certain sum as long as the limit of that list, that sequence of running totals, is whatever the number is. So I know that the limit as n goes to infinity of 1 plus 1 over 2 plus 1 over 2 to the n is 2, basically. And so what I say is therefore n equals 1 to infinity of 2 to the n minus 1 is the number 2. Now there's a proper word for this. I'm just going to look it up. Partial sum. Sorry? No, I'm not telling you how to figure it out. I'm just telling you what the answer is today because I'm doing an example to just make a running leap. Yep. Yes, totally is. That makes more sense. And this would be a half too. Sorry. This is the danger of being the second revision seminar of the day. David makes more mistakes. Yay, okay. Okay. That's the basic idea of series, is that I'm doing basically a running total of a sequence, and as long as that eventually stops somewhere, it'll be fine. So in my head, this picture is this. There's 1, and there's another 1. So there's 1, and there's an extra half, and there's an extra quarter, and there's an extra eighth, and there's an extra 16th, and there's an extra 32nd. And if I keep doing that, I'll eventually fill up the whole space up to 2. And that's the idea. Famous mathematician, philosopher in ancient Greece called Zeno had a paradox which went something like this. And if you want to get from 1 to 2, you have to go halfway first. So if you always have half left to go, how do you ever get there? And the mathematicians go, that's okay, just go forever and you'll get there eventually. They weren't as comfortable with infinity in ancient Greece. Ancient people of India, they were much more comfortable with infinity. Yeah. Okay. So, what we would like is to know whether a particular series that I could imagine actually represents an actual number. So if I can imagine going 1 plus a half plus a quarter plus an eighth and go, oh yeah, that's the number 2. And I want to know when I can do that. Because sometimes I could totally write down a series with like 1 plus, I don't know, 3/4 and plus 7/8 or whatever, and I can add up a whole lot of different things, or 1 plus a half plus a third plus a quarter plus a fifth. I could imagine something like that, and my question is, does that actually represent a number? And the fancy word we have for that is converge. And converge is used in the sense of getting closer to something. Things converge when they come together. So this is called, okay. This is called converging. See, I'm lucky and I'm at this end of the year and I don't have to define this for you for the first time. I can talk about it as if you've seen it before. So I don't have to give rigorous definitions for everything because they're in the notes. Okay, so I would like to know, how do I tell if a series converges? That's the big question. That's the question we all want to know, now that we know what a series is. And we've already found one that does. 1 plus a half plus a quarter, etc., comes out to 2. We want to know when that happens. When does it come out to some number at all? And, well, we're going to take the wisdom of the people who have come before us and learn from what they have to tell us. So, the first thing we're going to do is write down a list of classic series that the people before us have encountered, and they know what the answer is because they've figured it out before we got there. And so here's our, I call them the classic series. So classic series number 1 is the harmonic series. The harmonic series, well, I can write it, but it doesn't actually represent a number. This doesn't converge. I believe the word for not converging is diverging. It's not true everywhere. Some people in the world just have converge and not converge. So the harmonic series diverges. And as far as I'm aware, your lecturer will not expect you to prove that the harmonic series diverges in your exam. Pretty sure. Don't quote me, because I'm not running your course. But yeah, that series, if you do the running totals, it gets bigger and bigger and bigger, slower and slower and slower, but still gets bigger. I can make that thing, if I can pick a point and the running total can be as big as I want it to be as long as I add enough of them together. It will take longer and longer to do so, but that's not the point. Okay, that's classic series number 1. Classic series number 2 is something in this position to the power of n. And I'm going to start at n equals 0 as opposed to n equals 1 because that's convenient. This is called a geometric series. The series I had before was one of these. It started at half to the power of 0, which is 1, and then it had a half, and then it had a half squared, which is a quarter, and a half cubed, which is an eighth. That's a geometric series. So I know that some of the geometric series definitely converge, and there's a rule for telling whether it converges or not. If the x is less than 1, well, the absolute value of x is less than 1, then this converges. And if the absolute value of x is greater than or equal to 1, this diverges. And we're extremely lucky because it turns out that we don't just know that it converges. See, the fact that it converges is lovely. You say, oh yes, that's a proper number. Excellent. So David, which number is it? Oh, I don't know what that is. That's not helpful. Happens sometimes. But I actually know what it converges to. One over 1 minus x. This is one of the few that I know what the actual answer is when I add them all up. So if the size of x is more than 1, there is no answer. It doesn't converge. But if the size of x is less than 1, then it will converge to that answer. They're our classic series. There is one more. I'm just going to look it up and make sure that you've got it. There is a proof that it converges in the notes. So classic series number 3 1 over n to the power of p, which is called by many people a p-series. And this will converge depending on what p is. So we know if p is 1, it doesn't converge, because that's the harmonic series. So if the p is less than or equal to 1, it diverges. And if the p is greater than 1, it converges. But importantly, your notes and the universe in general does not contain a formula for what it actually converges to. We don't, for most of those, we don't have a formula for what the actual answer is. I believe when p is 2, like 1 over n squared, it converges to pi squared on 6. Okay. And my first year lecturer told me that with the words, and that converges to pi squared on 6, and I think that's just ace. I love Nick Bookdale. Anyway, he's very excited. So there we go, that's what it is. So for example, okay, so these are our classic series. These are the only ones we know of, pretty much. The ones that we can just look at, and you can just look at it and go, yes, that converges. Yep. Oh yeah. All right. This is the alternating harmonic, which is like the harmonic except that it switches between plus and minus 1 on the top, and that converges. It might start with an n plus 1, it doesn't really matter. And I believe that converges to ln2. Or minus ln2, depending on whether you've got the minuses in the right way round. Okay. And there is one more which I'm getting ahead of myself in, but I will put it in. The Taylor series for anything that's really nice converges. That, which is the Taylor series for e to the x centered at x equals 0, that converges no matter what x is. And it converges to e to the x. I'm getting ahead of myself here. Sorry. The Taylor's, that thing, x to the power of n over n factorial, that converges no matter what x is, and it converges to e to the power of x. And we get that from Taylor series, which is sort of later than this, or possibly before. I don't remember. It used to be before this in the old Maths 1B, and now it's after. Okay. But it's good to know, because the person who's writing your exam wrote it from the perspective of you having seen the whole course. And so it won't necessarily be in the order that the course is in, and you may be expected to join bits of information together from different parts of the course. And so this is a series, and you were told about it later, but it still is a kind of series that you're supposed to recognise. So there you go. So those are our classic list of series. If you see any one of those, then you can go, oh, I know whether it converges or not, because look at it. It's a harmonic series. Or, oh, it's a geometric series. So almost all of the methods that we have for dealing with series actually are about us comparing it to one of these. Yes. All right. So we have our standard list of series, and we would like to know, if it's not one of these on my list, how do I tell if it converges or not? So then we have some tests which have changed names. So we have some tests. So my first test is not called a test in your notes. In your notes, it is called by the helpful name of property 2.3. But the full name is the necessary condition for convergence. No one expects you to remember the number of the property or the theorem. You're supposed to remember it by its name. So in some places in the world, this is called the divergence test. And the necessary condition for convergence says that if it converges, then the limit of the individual terms, not the running total, not the partial sums, but the individual bits that you add, the limit of those has to be 0 or it can't possibly converge. So if you're supposed to be at 3? That's not what my timetable says. Okay, I'm just going to finish this sentence. So if the limit of the individual terms isn't 0, then the sum does not converge. So it doesn't tell you whether things do converge. This one tells you what happens when they don't. So if they do converge, that limit does actually have to be 0. But if they don't converge, if that limit isn't 0, they can't possibly converge.